This is the third week of COM S356F, Software Engineering and Project Management. We're on to Chapter 3 of the textbook written by David Kong. This chapter is about system engineering. So, last couple of weeks, we have learned the term software engineering, which cover a bigger scope than computer science. It's almost, very roughly, you can think of software engineering being computer science plus people, okay, people issues, considerations for people, people factor of how to develop things, how people work together as a team, and so on. Okay, so it's not, computer science is very, very technical, but software engineering cover more people aspect as well. So now we have another term, system engineering. Its scope is even bigger than software engineering. Why? Because, well, it's not just about software. It also covers hardware and also how the process people work together. So each different subsystem can work together. Okay, so there may be a hardware component, software component, actually many of those components. So that makes system engineering something that cover software engineering, like with a bigger scope, and as a result, it is a multidisciplinary approach. Require that to develop a system. Okay, multidisciplinary. What is a discipline? Well, electrical engineering is a discipline, and mechanical engineering is a discipline. Civil engineering is a discipline, and psychology is a discipline because it definitely involves psychology too. So it's, think of yourself as, even don't just limit yourself to how to write program. As a IT professional, increasingly you need to deal with systems. So a systems itself is a set of interrelated, interacting components. A system can be big, it can be small, it can be complex, simple, natural, or man-made. It can be physical or it can be virtual. And these are some examples. The universe is a system. Our solar system is a system. An ant is a system, or the jungle that an ant live in, or the building that the ant live in, is also a system. So you can see, you can construct a bigger system using several smaller systems. Okay, so sometimes we call those smaller systems as subsystems. So each system can be a complete system by itself, or it can be a part of another bigger system. So in that case, that part, we can call it subsystem. For example, sprinkler system, maybe there is that part that supply the water. Okay, sprinkler is the 灑水系統. Okay, on the ceiling of an office building, we may have some sprinkler that there may be sensors somewhere. It could be nearby, or actually right on the same device, that sense the heat, and then there's the water of supply, and there may be some mechanical device that would open and close depending on the temperature detected. Okay, and the telephone is a system that consists of base station as well as the phone. Okay, so but a phone itself, you can also consider it a small system by itself. So these are some example. This you can see a cell phone being taken apart with batteries. So a battery we can almost consider it a system by itself, although it's a little bit too simple. But then there is this phone itself is a system. Okay, but you can take a phone here to the telephone network. So this cell phone communicate to this base station, and another telephone is communicating with this another base station, and these two base stations may talk to each other, allowing the two mobile phone users to talk. So in this case, we have base station as a system, phone as a system, but then together many base stations and phone together form a big system. And the system will have to work with the environment. Okay, this is, in case you don't recognize this looks like a lawn mower. Okay, 剪草機. Okay, and I don't see any handle there. Looks like this is a smart one that will actually watch out for those things, because the one that I have used have a long handle here for a user to push and also avoid mowing the flowers. Okay, we just want to cut the lawn, we don't want to cut the flowers. So this looks like a one that is a lawn mower, 铲草機, that is smart enough to observe and interact with its environment nicely without cutting the flowers. And of course, the system can involve. This is the old mobile phone, so big, so heavy that you can actually use it as a weapon. And I think I probably have used something like this before. This is some older one. This looks like an Ericsson phone. And this looks very much like a BlackBerry. No, I'm not sure. I'm probably wrong. And of course, this is an Android one. So systems can evolve. So go back to the term systems engineering. Lots of time with people we use plural here. Okay, systems engineering. It covers entire life cycle. So from the birth to maintenance mode, or even retirement being replaced by a new system. So system engineering deal with all aspects of perceiving a system, creating it, putting it in use, and modify it for enhanced move, and then, or if it's not modifiable, if it's too old, then retire it, like to kill the system, like gracefully, so that with a good replacement in place. And system engineering usually take top-down approach. Divide a big task into small tasks, or divide a big system into components, and then you build the components and fit the components together. That you create a system. Okay. Interdisciplinary means roughly the same thing as multidisciplinary. Okay, that means you use knowledge more than one thing. Okay, it's no longer limited to software, because thanks to our advanced technology, software exists in everything now. All the physical things, they used to be, for example, in the old days when I was a kid, not everyone has a phone at their house, and even if they do, they are mechanical device. There's no software. Okay, it's a very simple mechanical phone. Even the lawnmower I used was a mechanical one, but now everything has some, increasingly more and more things has software component. So you as a software developer, software engineer, you cannot see your world being limited by software alone. You need to look at the bigger scope. Otherwise, your career, your promotion will be limited. Okay. With engineering process, well, engineering process emphasize systematic. You follow some methods, and you have some ways to measure quality, to ensure quality. So that is some characteristics of an engineering process, and it's top down. Okay, you have the big goal, a big system, you divide it into smaller system until each component is so small enough to be built, that you know how to build it, then you fit them together to form a system. Multidisciplinary teamwork. So, as you can see right here. Okay, this diagram, unfortunately, many of you are still waiting for the textbook, which is back order. The textbook has more point-by-point description of each of this. For example, system requirements definition on the textbook, the bigger diagram you will see, it involves identifying the business needs, defined system requirements, conduct feasibility study. To see the word feasible, I've mentioned it many times, you should know it by now. Feasible means doable, okay? Not infeasible means not doable. Okay? Sometimes some people may have a bright idea, but then maybe with the current technology, it's not doable. Okay? And then at the end of this system requirements definition, you produce a project plan. And there are these other activities you can check, and I won't go through that one by one, but you can. There's the legend. Sometimes the problem with drawing diagrams is that people may not understand what a line means. So here the author provide a legend saying that this means interaction. Software development interact with hardware development, and then it interacts with human resource development, meaning training the user on how to use it. Okay, and this solid arrow means workflow. So the activities of system requirements definition do work for the next kind of activities, modeling and design, and so on, and then go on to development, and then now you have different components, because this have many components, some software, some hardware. You integrate them together, then you test it. Okay, and if it's successful, you deploy the system. Deploy means hand over to the users to use it. Then once it's in the hands of the user, then from time to time, if you find problems, then maybe you need to do maintenance work. Okay, this is what roughly the word maintenance means. Okay, some physical system like this, the maintenance may mean you need to add oil somewhere. Okay, add oil to lubricate some moving parts. Maybe the moving part need lubrication. Beyond what? Okay, and so the parts may be moving, and if it loses lubrication over time, then there would be more wear and tear. So maintenance for physical system may have something like that. In fact, if you know about cars, automobile, you know every several months, half a year, you generally need to change the engine oil to make sure that there's clean oil that's effective for lubrication. because the car engine can revolve several thousand per minute. So you need to keep it nicely lubricated so that the parts don't break down. Okay, so that's. But of course, when it comes to software, it often means uh, adding fixes to some bugs or adding small new features to make it work better. System requirements definition. It, it involves identifying business needs and defining system requirements. What is a business needs? Well, usually there is current situations that you don't like about, okay, or the customers don't like, and you have a goal, okay, that is the ideal situation. So there's the current situation, not so good, and the ideal situation that's better. At that, we can also call it business goals. Then, by bridging the current situation to the ideal situation, you are meeting a business needs. You meet the business needs. So, but of course, before you do that, you need to identify that. So, think in terms of that. It helps. This thinking also can also help you if you are, let's say, selling something to a customer. Okay, you describe what's so bad about the current situation, and you try to convince them uh, what is the nice situation would be, and then you convince them, okay, you can provide this, and this is how uh, this roughly is the requirement stage. That's what you do with the requirements. So you define it, and only a subset of needs is satisfied by the system due to budget and schedule constraints. So there, this is like prioritization. You prioritize many needs and identify the one that is most important, most promising, okay, and also perhaps least costly to implement. And you build the product. So this slide describes the information collection for the uh, system engineer to talk to the customers. Okay, so these are the questions they will try to answer, or he's going to ask, "What's the business? For is there anything to automate? Um, what's the business context? What's the current situation? What's the new situation? The new goal you want to achieve?" Um, so this to learn more about the business. Sometimes uh, don't just listen to the customers. Maybe as a system engineer, you should visit the customer's site to go to the place they run business. Then you may have a better idea, because when someone describes their problems to you, um, for example, if a student come to me, uh, I've been doing this, I've been doing that, but I still don't, my uh, grades are still poor, I still don't do well. If I just listen to what they tell me their problems, I may not have the whole picture. It may actually be better if I can actually observe them, what they were doing uh, when they were studying. Okay, maybe they were studying in a distracted environment that they don't know about is causing the problem. So you need to visit the customer's business venue to learn. Um, Learn about the business processes. Okay, so identify the problem with the current system. If we don't have a problem, we have nothing to fix. But of course, there's usually some place you can improve. And so who are the users of the current systems and the future system? The user characteristics help you design a good system that's easy to use for them or efficient enough for them. Okay. You need to know about your customers' priorities and quality, performance, security. These are generally called non-functional requirements or quality requirements. These are some methods to collect information. A customer may make a presentation to tell you using PowerPoint to tell you about their business. Okay, you study their business operation, as I said earlier, perhaps visit. Okay, let's say if a restaurant have poor business and they hire you as a consultant, then maybe you need to visit their restaurant and see, or maybe you can just pretend to be a customer and then try to experience what it's like. Then before you can give advice, you can do some survey, give them an online survey or paper survey, or interview them, or you can study all the existing literature. This is called literature survey or literature review. Okay, you study what existing things about the business domain, but about the business. Okay, so for this chapter, many times the author used an airport baggage handling system to illustrate. Okay, so this system, ABHS, needs to handle check-in luggage. So when you go to the airline's counter, you give them your luggage, and you check in your luggage. Then they will need to send the luggage to the departure gate and baggage claim areas according to the destination. So after you give them at the check-in counter of the airline, you expect when you get to the destination, then you will be able to get your luggage back. So that is the end-to-end operation. Okay. There are other requirements. Airline sometimes, if someone cannot find it at the luggage claim place, then an airline agent need to figure out where it is. Okay, and also sometimes it happens that someone, if a passenger checked in their luggage, but then they never board the airplane, so they need to be able to identify where it is and then take it out, which bin even after it's been loaded in the airplane. Okay. And also some process may require it to go through some x-ray or something to detect if there's any dangerous items. And also for an airport, you need to know how many passengers you can handle. Apparently this is a system for a very small airport. Okay. In Hong Kong, you're used to a big international airport, but in other countries, there are many small airports that maybe only have several planes in an hour. Okay. So that's it for section 3.1 to 3.3.